In this lecture, I will continue our transport layer discussions, and specifically we'll talk a little bit more about efficiency of reliable data transfer. Last time, in last module, I mentioned that implementing very simple reliable data transfer over unreliable links, if we just have one single packet, can result in very, very bad inefficiency. And I showed you it's like on order of 0.0 many 0% of efficiency if you send in a single packet over a reasonably high RTT link, and highlighted that in order to improve efficiency, you actually have to have so-called a pipeline. And on this slide, I also kind of copy-pasted the slide from the previous module to highlight how can you improve efficiency and how you can calculate kind of how many packets you need to in order to have efficient data transfer. A few things to note about this thing. First of all, this number of packets that needs to be kind of in a flight at any given point of time actually variable. It really depends on the number of round trip time and the transmission delay. And both of these parameters can technically change. Kind of both depend on kind of bottleneck, how many packets already been in network, how many packets flowing across the network, not just from you, but from somebody else. And kind of all these parameters can cause number of packets that you need to adjust eventually. And of course, there's another meta parameter in this discussion is how many packets you actually, the amount of packets you push into the network, because in some cases you can cause the congestion collapse. Like we send in too many packets, everybody sending too many packets, and eventually nobody get any acknowledgements and only send in retransmissions. And just a reminder, when I talked about very simple data transfer, just when we had like a pipeline of one, even in that case, we already introduced the concept of sequence numbers. So in that case, we use the sequence number 1 or 0 to distinguish between a new packet from on the receiver side and retransmitted packets. Otherwise, there's a kind of uncertainty what exactly you packet, uncertainty exactly which packet you receive. Something similar going to happen with the pipeline more than one. To bootstrap our conversation about efficient, reliable data transfer, we're going to talk about the go back N approach. Specifically, this is the algorithm with a static pipeline. So this N is a kind of flow control window size, or the number of packets that you can send out and waiting for the acknowledgement to arrive. In this specific case, similar to what we had before, the minimum number of packets, number of sequence numbers is actually twice as many as the number of packets that are allowed to be outstanding. And similar as we did before, we can use sender timer as a kind of safeguard mechanism against lost packets. And for the feedback, in this approach, we're going to use this cumulative ACK, meaning that we're going to send packets, send acknowledgement for the latest acknowledged packet. And this information will also serve as a kind of some form of a negative acknowledgement, like if you properly interpret this information. In a lot of our future discussions about the reliable data transfer, and specifically for TCP in even our project 2, I'm going to be using the word window, and there's like a different association with the window. In this specific case, what I mean by window is actually the number of packets that can be sent out without waiting for the acknowledgement. And the key or interesting part of this window, sometimes referred also as a sliding window. So as this window effectively slides over the sequence numbers that you have. So if you have just a minimum amount of sequence number to n, so this window just be sliding back and forward and kind of sometimes overlapping. And if you have like an infinite number of sequence numbers, like in a theoretical case, so this window will gonna slide over packets that kind of were sent out individually, and as soon as something that I get acknowledged, this window being advanced forward by the amount of acknowledged packets. And to give you a very basic idea why exactly you have to have the number of sequence numbers twice as many as this kind of maximum size of the window, just consider this example. In this specific example, I picked only 4 sequence numbers and decided to use a window of 3. What you need to observe here is the there are different actions that happened on the receiver side, like depending on what kind of feedback is being received. But you can also observe what exactly is happening on the sender side. So from the sender perspective, first 3 packets you just sent out, was a window of 3, so we're just waiting for the acknowledgement to happen. From the perspective of receiver on the right side, it receives a single packet, acknowledges this packet, and moves its own internal window. It's acknowledged it received the second packet, send acknowledgement, and advanced its own window. Again, the same thing for the third packet. So from the perspective of receiver, whatever new packet arrives with the sequence number 1, 0, and 2, so those would correspond to either, if it's 0, then it's a kind of retransmitted packet. If it's 1, it's again retransmitted packet. But if it's 2, it would assume it's a new packet, because that's the only thing it can assume, because it's already advanced its window far enough. However, in the first case on the left side, it's actually did it quite a bit differently. So from the receiver perspective, yes, everything stays the same. It's received all the packets, it sent acknowledgement to all the packets, but different thing happened on the sender side. So the sender side now didn't lose the acknowledgement, but rather received the acknowledgement for the received packet. It may or may not send out the next packet, and then receive the acknowledgement, advanced the window, and maybe advanced window again. Now, if it sends the packet with a 2, 3, or 0 sequence number, again, from the perspective of receiver, it will be the new packet, and in this case, it happened to be the correct action, which is completely contradicting to what happened on the right side. So if you kind of play with a few examples, you actually realize, so to reduce all this ambiguity, you have to have as many sequence numbers, like in addition, in the reserve, to make sure that you never, even like whatever, receiver advances window and sender doesn't advance the window. So you have to have a distinguishment between all the packets that were sent out and the new packets that, and the packets that potentially have been received and the window has advanced forward, and expecting new packets to arrive. So I hope I got some form of illustration of that, that it wasn't too confusing for you. To illustrate the same with a slightly different example and a small animation, just consider, again, in this case, window size of 4, and somehow we decided to pick the also 4 sequence numbers. So initially, if you send everything, the sender will advance. And again, each time you advance, something will happen. However, as soon as the receiver advanced, it doesn't mean that the sender also advanced, because in order for the sender window to advance, it has to receive the acknowledgement, and there is no way for the receiver to know that the acknowledgement has been received, and in fact, there's no way to know about this. So it has to have advanced its own window and kind of have additional reserve and sequence numbers to make sure that this advancement doesn't contradict to anything that may or may not happen at the sender side. To highlight the finite state machine for the reliable data transfer, if we consider infinite buffer, then we can consider this relatively small example where we have only one state, but this is kind of a little bit overloaded state because we have a bunch of actions happening all the time. So in this case, we have to initialize this buffer, that is buffer that we store packets that we're potentially going to retransmit over and over. We have also the infinite sequence number and some kind of a base. So note that this parameters actually needs to be synchronized between sender and receiver. Like we assume in this example, they're not synchronized, but in real example, in the real protocols, these numbers have to be synchronized. And kind of the 3 actions that are happening with the state machine is actually sending timeout and receiving the acknowledgement. And I try to highlight in this Python-like language what can happen when you do this. So for the first action, if you receive something from the application to send packets, so we first, as a first action, we buffer this packet. And if we have enough space in our window to send packets, so this is kind of representing base plus n and the next sequence number, we simply start sending the packet and advance the next sequence number. So like the next time something called the function, we can kind of use the proper sequence number. One thing that is in addition here is one additional condition to start the timer. If you kind of analyze this a little bit more, you will notice that there's only one timer at a time. So whenever you send 100 or 5 or 3, if you packets at a time, so if you end 500 or 3, there will be only one timer. And this timer is effectively very, very like rudimentary, coarse, granular timer representing something really bad happened in the network, and you didn't receive any kind of acknowledgement. So whenever this timer happens, what we try to do, we simply go back n, so simply retransmit all n packets that we had before. If you had less than the n packets, then you will transmit the less n packets, but if you have as many as n, then you just retransmit all of them. And the final action is when we receive the acknowledgement, we stop the timer. So the timer now is actually acting as a just kind of heartbeat. So whenever we receive the acknowledgement, we stop the timer and potentially restart the timer. And the other action is base equals sequence numbers plus 1. Simply it means that if this is the really cumulative acknowledgement, meaning the sequence number in the acknowledgement is the one that the receiver has received up to this point, like in order. So as a sender, you can simply forget about earlier packets and just assume this is the new base. And finally, if the base is less than the next sequence number, meaning that you're still waiting for the acknowledgements, we restart the timer. And if some of the acknowledgement didn't come, they will be effectively cached by the timeout. However, our buffer is not really infinite, but we can actually very easily convert our infinite buffer to finite buffer simply by using a modular logic. So you still have to have a reasonably sized buffer in range of 0 to m, which m represents the amount of data that you're willing to accept. So this m has to be more than n, but how much more than m, it really doesn't matter. In your project 1, several of you have tried to set a very, very high buffer size. So that buffer size that you send is exactly this number of m. By the way, the amount of buffer you set in the project actually didn't really make any difference. So you shouldn't really change the buffer or set it to any large value in order to accept big files. So in order to accept big files, I think most of you have realized, you simply have to call receive multiple times and kind of call it until you get the data, all the data from the socket. So again, just small sidetrack. And simply by using this modular operation module m, you can easily kind of deal with it just with this buffer, with this limited buffer, because as soon as your site wraps up, you're going to be always operating kind of on the new sequence numbers. In this example, I'm not showing you how to wrap up this sequence numbers, but the logic would be approximately the same. You're still going to be using the modular logic, and whenever you wrap up, you can just change the sequence number to the new numbers. And this is exactly what happens in TCP and what you will be doing as part of the project too. And if you have more questions about this, how exactly to realize, please free to ask me over email or on Piazza. The receiver side is actually not that complex. It's still receiving data and sending out acknowledgements, and it's about the same complexity as it was in the previous examples. There's an ability to improve a little bit efficiency a little bit more by having so-called a selective repeat. So instead of literally retransmitting everything that was sent out before, like last n, you could retransmit only the things that you think were lost in the process. In order to do that, the sender actually have to buffer packets. So the previous example that I show you, it received the packets. If something was not delivered in order, that packet was simply ignored. And kind of by sending the acknowledgement for the previous sequence number, or like to the previous to the expected sequence number, we indicated that, oh, we didn't receive anything, so please retransmit eventually, maybe on a timeout. And if you receive in order, you send the acknowledgement of that packet, so kind of the sender can continue sending. So in this example, we expect in sender to retransmit all the packets if some of them lost or acknowledgement were lost. With selective repeat, we're trying to optimize a little bit and ensure that the sender is not sending packets that were not lost in the transmission. So to realize that the sender, as I said, will have to have some form of a window, and this window have to be just n. So unlike the sender side, it doesn't have to be really large, and it really depends on nothing except this value of n. And whenever you receive packet that is in order, you simply advance the window in the same way you advance the sender window over the sequence numbers. If you receive packet that was out of order, you simply receive the packet, but you kind of don't advance the window and you're expecting the packet to arrive. What you send in response really depends. So you could send, there are different mechanisms. You could send simply the same cumulative acknowledgement and rely on the sender side to infer from those cumulative acknowledgement which packet was lost. So sometimes it's possible, sometimes not really. Or explicitly tell that, oh, I received this packet, but I didn't receive the previous packet. So that would be like selective acknowledgement. It's not required for the selective repeat, strictly speaking, but you can assume either of these two cases. So yet another way of realizing this part, like as illustrated in this finite state machine for selective repeat, is to simply associate timers with each individual packets. So again, this is not normally how TCP is realized, but it's one of the way you can accomplish this. So, and the only modification for the original RDT send action is setting up the timer for every single sequence number. For the timeout action, there's actually quite a bit of difference because now we, again, restarting the timer and sending out only the packet that was timeout. And finally, on the acknowledgement that we're receiving, we stopping the timer and kind of only restarting that timer that we kind of next sequence number that we're expecting. There could be some small bug in this case, but this is just highlighting the overall idea what exactly is or can happen in this environment. For the receiver, picture is quite a bit different. Unlike the previous example where we just had very simple kind of logic for receiving data packets or in order and out of order, in this case, if you receive out of order, you have to buffer this packet. And if you receive an in order, you will have to kind of check whether the packet fills the hole like that was received. If it fills the hole, then you have to deliver to the application everything and advance the whole window. If you didn't receive in order or just receive only one packet in order, then you just advance this window by one and continue operation, continue waiting. So this is a little bit of complexity involved, but you potentially significantly improve performance in very, very bad cases. Again, all these kind of improvements are for the cases when packets are lost. And if there are not too many packet losses, even the go back N will give you reasonably good performance numbers. If you have a very big number of losses, then selective repeat or additional approaches that we'll discuss in TCP would provide much better resiliency or much better performance parameters. And the selective repeat in action, this is just to highlight what exactly happened, kind of what could happen if you have, like, for example, 8 sequence numbers and window size of n. So we can, so we're sending out these 4 packets. For each packet, the sender associates the timeout. And receivers send out acknowledgement, not sending out acknowledgement. This actually doesn't really matter from the sender perspective. But as soon as the packet 2 that was lost, the timeout happens, then it will retransmit the packet, it fills the hole on the receiver side, and receiver will send happily the acknowledgement, cumulative acknowledgement of everything, and the whole process will continue smoothly afterwards. So it's a kind of very nice, very simple way of realizing kind of faster recovery, like more space efficient in terms of number of packets sent out. To make sure that you really understand what is happening in the system, like with the pipeline, let's do one more exercise, like as your homework. So let's first assume there are 3 packets in a pipeline. So there's a pipeline of 3. We're using go back N. We have no packet losses in the environment. So, and I want you to calculate the effective throughput. Not the efficiency as we calculated last time, but rather, or utilization, but rather what would be the effective throughput in this specific case. And effective throughput is what is like on average how much data we can push through. And you can assume the header size is 0 in this case. And the other question, which is kind of inverse, is what would be the window size that correspond to full utilization, or to make sure that you use all this 1 megabit per second link. And to give a kind of basic summary of what I just talked today, so to make sure that we have efficient data transfer, is not just we need to ensure that every single data packet that we send out is acknowledged, but rather we need to allow multiple packets to be sent out without being acknowledged. Otherwise, we simply don't have time to kind of don't give network enough work to do in order to kind of fill all the pipes, in order to compensate for the delay for the sending packet back and sending packet and receiving the acknowledgement. There are multiple ways that you can realize this so-called the pipelining. And in this lecture, I talked about the two of them. One very simple was go back n, where we sent out n number of packets, and we waited for the acknowledgement. If something bad happened in the network, some packets are lost, then we retransmit all these last n packets. With a bit of improvement, we had the selective repeat when we associated timer with every single packet sent out. And when some bad things happened in the network, we retransmitted just one of those packets. So this is a very basic mechanism that we talked before. There are many more you can imagine, and TCP is yet another way, which has a little bit additional mechanism to infer what has been lost without adding this additional complexity of having timer per single packet, because it's quite a bit expensive, and people in kernel, like in Linux kernel, for example, don't have enough memory, and they try to optimize, they try to reduce number of whatever state is being kept per active TCP connection. And with ideal pipeline, there is a dependency of a number of packets needs to be sent out before being acknowledged. And this number is, as I said, not static, but rather depends on the RTT and the transmission delay. And all these parameters being varied. And to realize the realistic pipeline, you actually have to do this estimation. You have to estimate RTT, and you have to estimate retransmission timeout. And kind of for this one, I will ask the question online. You have to estimate the bottleneck, actually, because you don't want to send too many, even though even you may decide that you need to have like 100 of the pipeline in order to kind of fill the pipe. The network maybe at some points of lifetime of this connection may not have enough capacity to support all these 100 packets that you want to send out. So you may need to cut stuff. And finally, you don't want to send too many packets if the receiver being overwhelmed. For example, if receiver is doing very slow processing, very slow acceptance of packets, then it may be the case that you can only send 5 instead of 100. So this is another thing to consider as part of this reliable data transfer, or so-called receiver flow control. And I will talk more about this in the next part of the lecture. Okay, I hope it was interesting, and see you next time.